The screen opens on silence, not an ordinary silence, but the kind that seems older than time itself. A silence stretched thin across the fabric of eternity. Far away, starlight flickers through a haze of cosmic dust, rivers of light drifting like ancient thoughts through the dark ocean of space. Between those rivers, shadows move, vast, unseen, patient. In that darkness hides the universe's strangest secret, not in the glow of galaxies, not in the birth of stars, but in the voids between them, places where light itself dares not return. There, in the unseen heart of gravity's deepest pull, the known laws of physics begin to tremble. Scientists call them holes, but they are not mere absences. They are wounds in the structure of reality, places where gravity folds space upon itself, where time curves until it forgets how to move forward. Some are thought to connect distant regions of the cosmos. Others, perhaps, open into entirely different realms of existence. Here, the equations of Einstein strain under their own beauty. Quantum theory, our most trusted language of the small, loses meaning at the edge of infinity. It is a frontier where knowledge dissolves, where reality itself seems to hesitate somewhere. In that hesitation lies what physicists quietly call the most mind-blowing hole in the universe, a place where black holes meet quantum mechanics, where space-time might tunnel, ripple, or even split. And so the question remains, suspended like starlight over a black horizon, what lies beyond the edge of falling? And if the universe can open such a hole within itself, what does that say about the fragile reality we live inside? The starlight fades, the silence deepens, the journey begins. The idea of a hole in the universe did not begin with Einstein, nor with the telescopes that now stare into black horizons. It began in the candlelight of the 18th century, when the cosmos was thought to be infinite yet ordered, lit by countless stars that burned without end. Among those early dreamers stood an English clergyman named John Michell, a man of quiet calculation and extraordinary foresight. In 1783, long before the language of relativity or quantum theory, Michell imagined a star so massive, so heavy with its own gravity, that not even light could escape. He called it a dark star. The idea was almost heretical, a paradox before physics had the tools to explain it. If light could not flee, how could such a star ever be seen? And if it could not be seen, how could it be known? Michell's thought faded into obscurity, surviving only as a whisper in old philosophical letters. But his vision marked the first shadow of something extraordinary. The recognition that gravity might not only hold the universe together, but could tear it open. Decades later, another mind touched the same darkness. Pierre-Simon Laplace, the French mathematician who saw the universe as a vast machine of precision, calculated that a body of sufficient density could indeed trap its own light. He wrote of this possibility with mathematical elegance, but it too was forgotten. The age of Newton's clockwork cosmos could not yet accept such monsters. The universe was a place of order, not of holes. For nearly a century, the idea slept, a seed buried beneath centuries of certainty. Then came Einstein. With the dawn of the 20th century, he redrew the very fabric of the cosmos. Space and time were no longer separate. They were one continuous fabric, bending and curving under the weight of matter. Gravity was not a force, but a geometry. And in that geometry lay the key to Michel's ancient dream. Einstein's equations of general relativity, published in 1915, described how mass tells space how to curve, and how space tells mass how to move. They were equations of profound beauty, but also of danger, for hidden within them were solutions that defied intuition. Einstein himself saw only harmony in their form. He did not yet see the abyss waiting behind them. Far from the safety of Berlin's lecture halls, a soldier lay dying on the Eastern Front. Karl Schwarzschild, an astronomer and physicist serving in the German army, read Einstein's newly published papers between battles. In the trenches of World War I, under skies torn by artillery fire, he performed one of the most elegant calculations in the history of physics. He found an exact solution to Einstein's equations, one that described a point where space-time would collapse into infinite density. He had discovered what would later be called a singularity. Schwarzschild's letter reached Einstein in 1916. The equations were flawless, but they carried within them an unsettling prediction, a boundary beyond which reality itself would vanish from view. Einstein praised the work, but rejected the possibility that such an object could truly exist. He thought nature would prevent such an absurdity. Yet the mathematics stood, cold and unmoving, like a mirror to something the universe was not ready to reveal. Schwarzschild died soon after, weakened by disease from the war, but his final calculation became immortal. The birth cry of the black hole, though that name would not appear for another half-century. What his equations described was simple, yet terrifying. A region of spacetime so dense that escape velocity exceeds the speed of light. A place where all paths curve inward, where even time itself falls and never returns. The world was not yet prepared to imagine such an abyss. For decades, physicists treated Schwarzschild's solution as a mathematical curiosity, not a physical reality. But some minds kept wondering, if nature allows such extremes, could there be more? Could space fold, not merely collapse? Could gravity create not an end but a bridge? By the 1930s, Einstein himself returned to this dark frontier, joined by his collaborator Nathan Rosen. Together, they explored what happens if two Schwarzschild geometries, two black holes, are connected at their singularities. Their calculations revealed a passage through space-time, a tunnel linking two distant regions. They called it the Einstein-Rosen bridge. Later generations would give it another name, wormhole. It was the first whisper of something stranger than any star, stranger even than a black hole. A structure that could connect the farthest reaches of the cosmos, or perhaps even two universes. To visualize it, imagine space-time as a sheet of fabric. Place two distant points upon it, and instead of traveling across the surface, fold the sheet until the 2 points touch. That fold, that impossible shortcut, is the essence of a wormhole. Yet this bridge existed only on paper. Einstein and Rosen soon realized that such a structure could never remain open. It would collapse instantly, faster than light could pass through. The tunnel would close upon itself, sealing the connection forever. Still, the seed had been planted. For the first time, physics had written a doorway into its own equations. Years later, in the mid-20th century, as the theory of relativity merged uneasily with the new quantum world, the idea of holes deepened. Physicists began to see the vacuum of space not as empty, but as alive, a restless sea of energy, where particles flicker in and out of existence. And if space-time itself could ripple, stretch, and bend, could it also tear? Could microscopic wormholes flicker into being at the smallest scales, forming and vanishing in quantum foam? The question reached beyond mathematics, into the realm of metaphysics. If space could connect itself across impossible distances, then perhaps the universe was not a flat expanse at all, but a living network of folds and tunnels, a grand architecture of connection. The human mind, still anchored to the visible, struggled with the implications. A black hole already defied the senses, an object that can be both infinitely small and immeasurably massive, both present and hidden. But a wormhole, a bridge through space-time, implied something even greater. It hinted that reality itself might be threaded with unseen corridors, that the cosmos, instead of being one continuous expanse, might be a woven tapestry of multiple realms. Einstein, cautious and weary of speculation, withdrew from the idea. He believed the universe was elegant but not mischievous. Others were less certain. Decades later, the same geometry that haunted Schwarzschild's dying thoughts would inspire generations of physicists, John Wheeler, Kip Thorne, Stephen Hawking, to reopen the equations and ask, what if the universe truly allows tunnels through its own flesh? But in these early years, when the first shadows of the impossible appeared, the discoveries were not yet technological. They were philosophical. They forced humanity to confront a truth that echoed through every century of science. That reality may be far stranger than it appears, and that every new theory brings us closer not to certainty, but to wonder. The darkness that Michel imagined as a dark star had evolved into something much more profound, a window into the structure of space-time itself. The cosmos was no longer a static stage. It was alive, dynamic, capable of collapse and rebirth, of bridges and barriers, of mysteries that curve beyond comprehension. And so, in dusty notebooks and trembling equations, a pattern began to emerge. Gravity was no longer merely a force that held things together. It was a storyteller, writing, erasing, and rewriting the architecture of the universe. In every collapse, there might be a rebirth. In every ending, a hidden beginning. The early dreamers could not have known that centuries later, their equations would be tested not by candlelight, but by telescopes orbiting distant worlds. They could not have imagined the Event Horizon Telescope capturing the first real image of a black hole's shadow, nor the gravitational waves rippling through spacetime, whispering the echo of colliding singularities. Yet the thread that connects those modern marvels began here, in Michel's quiet speculation, in Laplace's forgotten footnote, in Schwarzschild's dying letter. It is a story not of sudden revelation, but of endurance, of how the smallest idea, once dismissed, can survive across centuries, waiting for the right moment to be seen again. The narrator's voice softens. Humanity has always searched for light, but again and again, it is in the darkness that it finds its reflection. The holes, once imagined as cosmic absurdities, are now among the most real, most powerful structures in the universe, but they are not alone. Beyond the black horizon lies another possibility, not a hole that devours, but one that connects. And so the question returns, quieter now, yet heavier. If gravity can create a bridge instead of a grave, if space can fold and touch itself, what does that say about the limits of the universe? What does it say about the limits of the human mind? For within the equations of dying men and forgotten scholars, the cosmos had begun to reveal its first true paradox, that to understand light, one must first look into the deepest shadow, that the path to knowledge begins not with certainty, but with the courage to imagine the impossible. The darkness waits, vast, silent, alive, and the next chapter of discovery is about to open. For centuries, gravity was seen as a quiet, obedient force, a pull that shaped the orbits of planets, that held the moon in its path and the oceans in their tides. But Einstein changed everything. He did not see gravity as an invisible thread between masses, but as the very shape of existence itself. In his vision, space and time were not the stage upon which the universe performed. They were the performance, a flexible, rippling fabric capable of bending, stretching, and twisting under the weight of matter and energy. Mass told spacetime how to curve, and spacetime told mass how to move. This simple sentence would become one of the most elegant and most dangerous ideas in human history, because if spacetime could bend, then perhaps it could also tear. And if gravity could warp light, perhaps it could consume it. At first, the equations were serene, describing a cosmos of harmony and geometry. But when pushed to extremes, when the numbers were fed the enormous weight of a star collapsing under its own gravity, something broke. The mathematics began to twist upon itself, spiraling toward infinities that should not exist. Within Einstein's own equations lay the seeds of contradiction, places where time stopped, distance lost meaning, and density grew beyond measure. Physicists had stumbled upon the first boundary of reality, a place where even the laws that define the universe refused to speak. These singularities, predicted but unseen, were the ultimate shock to reason. They suggested that the universe could create regions where its own rules failed. It was as though the cosmos, in its vast perfection, had hidden fractures within its design, silent reminders that even order carries within it the potential for collapse. Einstein himself distrusted these infinities. He believed that nature, elegant and self-consistent, would find a way to prevent such absurdities. But the equations remained unflinching and unyielding. They told a story of impossible depths, of horizons beyond which not even light could return. As the decades passed, the mathematics began to evolve. Physicists re-examined the strange solution first glimpsed by Karl Schwarzschild during the war. They realized it contained not only a black hole, but something else hidden beneath. A mirror structure, a reflection of space-time itself. In 1935, Einstein, now working at the Institute for Advanced Study in Princeton, joined with a young physicist named Nathan Rosen to peer deeper into these strange geometries. Their goal was not to build portals through space, but to escape singularities, those intolerable infinities that haunted the equations of general relativity. Yet in their attempt to heal the wound, they uncovered something astonishing. By joining two solutions of Einstein's field equations, two symmetrical black holes, they discovered that space-time could connect them through a hidden passage. It was not a hole in space, but a bridge, a corridor through the fourth dimension, linking distant regions of the universe. They called it the Einstein-Rosen Bridge. For the first time, Physics spoke of tunnels through the fabric of existence, wormholes, as John Wheeler would later name them. Here was the first mathematical proof that space-time was not merely flexible. It was connectable, layered, and alive with unseen pathways. But the triumph was short-lived. When scientists tested the stability of the bridge, they found a fatal flaw. The tunnel collapsed too quickly for anything, even light, to pass through. The very act of opening the bridge caused it to snap shut, crushed by its own gravitational intensity. The universe seemed to forbid the crossing, allowing only the glimpse of what might have been. Still, the discovery changed everything. For the first time, the boundary between here and elsewhere blurred. If space-time could fold upon itself, what did that mean for the structure of reality? Could every black hole contain a hidden exit? A path not to destruction, but to somewhere else? The shock deepened with the birth of another impossible object, the white hole. Mathematically, it was the inverse of a black hole. Where a black hole pulls everything inward, a white hole pushes everything out. Nothing can enter. Everything is expelled. It is a region of space-time where time itself runs in reverse, where matter is forever escaping rather than falling. White holes were never observed, but they emerged naturally from the same equations that defined black holes. And that symmetry raised a profound question. If the universe allows one, must it not allow the other? Could every black hole, somewhere beyond its invisible horizon, be connected to a white hole? A mirror twin that balances the cosmic ledger. Such a bridge, a black hole at one end, a white hole at the other, would be a complete tunnel through space-time, a wormhole spanning the unimaginable. It would mean that every death in the universe might conceal a birth. Every collapse might hide an escape. But to cross that bridge would require breaking more than gravity. It would demand the bending of time itself. Physicists ran the numbers again. According to the solutions, time behaves differently near the horizon of a black hole. For an outside observer, an object falling toward the edge appears to slow, frozen in place for eternity. For the object itself, time continues normally, until it reaches the singularity, where all paths end. But if the other side of that singularity connects to a white hole, time would begin again, flowing outward instead of inward. A cosmic mirror, a rebirth of information. The implications were staggering. It suggested that black holes might not be tombs, but gateways. That somewhere beyond the event horizon, the matter and light devoured by one universe might emerge into another, perhaps even into the vastness we call our own, reappearing as distant bursts of energy, as the birth of new galaxies, or as the first sparks of creation itself. Such speculation bordered on the metaphysical, yet it was grounded in the cold precision of mathematics. The shock was not emotional, it was intellectual. Physics, once built on certainty, was now haunted by paradox. Einstein's equations, which had promised a unified vision of the cosmos, were revealing fractures, glimpses of something that defied every human intuition. Quantum theory made the fractures deeper still. When applied to the microscopic world, gravity's smooth curves collided with the jittering uncertainty of particles and probabilities. Space, once continuous, became granular, a quantum foam of fleeting energies and ephemeral connections. At that scale, wormholes might appear and vanish in moments, tiny tunnels flickering within the very texture of space-time, a universe riddled with holes too small to see, yet too fundamental to ignore. Einstein resisted such interpretations to the end. He preferred a universe that was real, continuous, and whole, not one built from chance and chaos. But the new generation of physicists could not turn away. Each paradox brought them closer to a deeper truth, that space-time might not be the foundation of reality, but a manifestation of something more fundamental. If so, then perhaps these holes, black, white, or microscopic, are not merely phenomena. They are windows into the source of existence itself. In the decades that followed, the equations continued to whisper their contradictions. For every solution that described order, there was another that described rupture. For every universe that expanded, there was one that folded. Physicists began to wonder whether reality was singular at all, or whether it was a vast network of connected domains, each born from the death of another. A black hole collapses in one universe. A white hole explodes in another. The bridge between them forms a pulse, a heartbeat of creation echoing through eternity. If that is true, then the universe may not be an island, but an ocean, one that breathes through these hidden tunnels, birthing new realms from the ashes of the old. And yet this remains only theory. The bridges cannot be crossed. The white holes cannot be seen. Even now, they remain ghosts in the equations, glimpses of something the universe hints at, but never confirms. Still, the mystery endures, growing deeper with every observation of the cosmos. Every time a telescope captures the faint glow of a quasar, powered by a black hole billions of light years away, the same question arises. What lies behind that darkness? What becomes of the light that falls and never returns? Perhaps somewhere, beyond the reach of even our most powerful instruments, that light reappears, released by a white hole in a universe not our own. Perhaps the universe is not destroying itself at all, but endlessly transforming, folding upon its own dimensions in a dance of birth and collapse that never ends. The narrator's voice fades into a whisper, as though spoken through the fabric of space-time itself. The equations that once promised clarity now open doors into vertigo. Einstein's gift to humanity, a vision of elegant simplicity, has become a labyrinth of paradoxes. Every line of mathematics reveals both a truth and a fracture. Every discovery deepens the mystery, and so, physicists stand at the edge of comprehension, staring into the strange geometries their own logic has drawn. The universe no longer behaves like a machine. It behaves like a mind, self-referential, recursive, haunted by its own reflection. If every black hole hides a white hole, if every singularity conceals a bridge, then perhaps the cosmos is not punctured by destruction, but by possibility. Invisible tunnels of reality, connecting not only distant corners of space, but the limits of what can be known. In the silence between equations, a question lingers like the faint hum of gravity itself. Is the universe filled with holes, or is it made of them? The age of silent equations gave way to the age of instruments, and with it, humanity began to listen to the whispers of the cosmos in ways it never could before. The invisible had always ruled the universe, but now, antennas of metal and mirrors of light began to reveal the shape of that invisibility. What began as abstract mathematics, distant, cold, and unseeable, started to bleed into observation, into data, into faint radio songs carried across billions of years. In the middle of the 20th century, the invention of radio astronomy allowed scientists to tune into a universe that had never known silence. Across this ocean of wavelengths, researchers began to detect strange, flickering pulses, quasars, sources so luminous they could outshine entire galaxies. Their origins seemed to defy common sense. Some physicists whispered that these blinding cores were powered by collapsed stars, black holes of staggering mass. Others hesitated, for to speak of black holes then was to court fantasy. And yet, decade by decade, the evidence grew harder to ignore. By the 21st century, the hunt for the unseen had reached a new horizon. Around the globe, a network of radio telescopes began to synchronize with exquisite precision. From the Atacama Desert to the ice of the South Pole, each dish became a fragment of a single colossal eye, the Event Horizon Telescope. In 2019, this global instrument captured an image that would haunt human imagination. The dark shadow of a black hole at the heart of galaxy M87, encircled by a halo of incandescent plasma, a portrait painted by gravity itself. It was not an image in the ordinary sense. No camera had truly seen it. What the world beheld was the reconstruction of a billion data points, light bent and delayed by the curvature of space-time. The black core was not an object, but an absence, the boundary where light could only orbit, never escape. The universe, for the first time, allowed humanity to glimpse the outline of its own mystery. But buried in that monumental success lay a whisper of strangeness. The luminous ring, thought to be symmetrical, glowed unevenly, brighter on one side, dimmer on the other. This asymmetry, though predicted by relativity, hinted at deeper turbulence, at physics pushed to the brink of collapse. The brightness could shift depending on the observer's angle, on the spinning of the hole, or on something even stranger, distortions that might emerge if the space beyond the event horizon were not simply an end, but a passage. Scientists like Kip Thorne, who once mapped the geometries of interstellar travel in theory, turned to the equations once again. Alongside thinkers such as Matt Visser, they began to explore the possibility that the Einstein-Rosen bridge, once dismissed as purely mathematical, might in fact find refuge in reality if one ingredient could be found: negative energy. In ordinary physics, energy is positive. It adds, it builds, it binds. But at the quantum scale, the vacuum is not empty. It seethes with transient fluctuations, particles flickering in and out of existence like fireflies in an unseen storm. These fluctuations sometimes create regions of negative energy, tiny voids that reduce the energy density of space itself. Quantum field theory predicts such behavior, though it remains fragile and brief, lasting only a heartbeat of Planck time. Yet in those flickers, some physicists see scaffolding, the faint architecture, upon which space-time tunnels might be stabilized. If negative energy could be harnessed, or if the universe itself already provides it in sufficient density, then the collapse of a wormhole might be resisted. A bridge through space-time, otherwise destined to snap shut faster than light could cross it, might instead remain open, a passage from one cosmic shore to another, sustained by the vacuum's own trembling. The mathematics of such a construct is brutal in its beauty. A traversable wormhole requires exotic matter with negative mass, a concept that defies all ordinary understanding. Instead of falling inward under gravity, such matter would repel. It would stretch the fabric of space outward, carving a tunnel between distant points. To exist, it would need to violate the so-called energy conditions of general relativity, assumptions Einstein himself had never thought to question. In recent years, physicists have begun to simulate such geometries using quantum computers and numerical relativity. In some models, space-time near a wormhole throat behaves not like a singularity, but like a mirror, bending light in peculiar lens-like ways. These distortions could mimic or even camouflage themselves within the patterns of gravitational lensing already seen in deep space. The light of distant galaxies could, in theory, pass through such regions and emerge twisted, doubled, or delayed, evidence not of a simple gravitational well, but of a curvature that loops back upon itself. Across the Milky Way's core, astronomers have long observed anomalies in the orbits of stars near Sagittarius A, the supermassive black hole at our galaxy's center. Most move with predictable elegance, obeying gravity's deep rhythm, but a few stars exhibit irregular accelerations, minor deviations, almost imperceptible yet persistent. To most, these quirks fall within observational uncertainty. To others, they could be whispers of unseen geometry, ripples of a throat embedded within the gravitational field. If such a tunnel exists, its mouth would resemble a black hole from nearly every observational angle, yet its behavior might subtly diverge. The absence of a true singularity, the possibility of information escape, the faint modulation of light frequencies that betray a passage rather than a prison. The evidence remains uncertain, suggestive, not conclusive, but in the frontier of physics, uncertainty is often the first step toward revelation. In the laboratories of thought and in the observatories of the world, humanity continues to trace these threads, from the quantum foam that froths beneath space-time's surface to the colossal halos of energy orbiting cosmic abysses. The question persists: are these anomalies the artifacts of extreme gravity or hints of a deeper architecture, an interwoven cosmos connected by hidden corridors? NASA's upcoming missions, alongside the next generation of telescopes like the James Webb and the planned Laser Interferometer Space Antenna, are designed to probe such possibilities indirectly, by detecting gravitational waves that deviate from the patterns predicted by standard black holes. A traversable wormhole, if one exists, would produce a distinct gravitational echo, a faint, secondary ring in the fabric of space-time, the aftervoice of a wave that has passed through and returned altered. These ideas linger at the edge of science, where mathematics meets wonder. Some physicists caution that wormholes, if real, would be violently unstable, devouring themselves before they could be crossed. Others argue that stability could emerge naturally within certain quantum gravity models, perhaps through mechanisms not yet understood, or through laws that only reveal themselves when the universe is viewed not as a collection of objects, but as a single vibrating field. Still, the search continues. The Event Horizon Telescope plans to image Sagittarius A, hoping to refine its vision of the invisible. If asymmetries or unexplained lensing patterns emerge again, if light appears to echo or refract in ways not predicted by relativity, it may force physics to reconsider the line between hole and bridge, between collapse and creation. The evidence remains spectral, faint, like the footprints of a dream in the dust of stars. But every observation brings the cosmos closer to confession. For now, the holes we see are still black, still devouring, And yet within their shadows, the numbers whisper of escape, of passage, of something beyond the fall. Perhaps one day, humanity will find not a singularity, but a door, the mouth of the universe's most mind-blowing hole, waiting to be opened by the patient hand of understanding. The narrator's voice softens, fading into the hum of distant galaxies. The question hangs, unresolved but luminous. What if the universe itself is stitched together by invisible bridges, and we have only just begun to see their shadows? There are moments in science when the universe seems to turn back and whisper, "You have misunderstood me." For decades, physicists had believed that black holes were simple in their cruelty. One-way traps from which nothing, not even light, could escape. A star collapses, gravity wins, and the story ends in silence. But in the 1970s, a young physicist in Cambridge began to question that silence. His name was Stephen Hawking, and his equations would ignite one of the greatest paradoxes in modern science. Hawking had noticed something subtle, a tremor in the mathematics of quantum fields surrounding black holes. Space, he realized, was not empty even at the edge of a black hole. It seethed with virtual particles, constantly appearing and vanishing in pairs. Under normal conditions, these pairs annihilate each other instantly, but near the event horizon, gravity could tear them apart. One particle falls inward, the other escapes outward, a ghost of the black hole's mass, leaking into the cosmos. This faint emission, now known as Hawking radiation, suggested that black holes were not eternal prisons, but slowly evaporating bodies. Over unimaginable timescales, they would shrink, fade, and vanish into nothing. The universe, it seemed, was reclaiming even its darkest secrets. But there was a problem, one that threatened the very foundation of physics. If black holes evaporate completely, what happens to the information about the matter that fell in? In quantum mechanics, information cannot be destroyed. Every particle's quantum state, its identity, must remain somewhere, encoded in the fabric of reality. Yet a black hole's final evaporation would seem to erase it utterly, violating one of the most sacred principles of science. This became the black hole information paradox, a question so deep it pierced the heart of both quantum theory and relativity. One theory demanded the indestructibility of information. The other described a horizon beyond which information could never return. Together, they created a contradiction, a cosmic standoff between the laws that govern the very large and the very small. Hawking himself wrestled with this paradox for decades. If the equations were correct, something fundamental had to give way. Either information was lost forever, or quantum mechanics, the most tested theory in science, was incomplete. For years, the paradox stood unsolved, haunting conferences and calculations alike. But as physicists pushed deeper into the mystery, strange possibilities began to emerge. Possibilities that made the universe seem less like a machine and more like an organism, capable of regeneration. Some researchers propose that as a black hole evaporates, it leaves behind not pure nothingness, but a remnant, a compact, stable object retaining the hidden information within. These hypothetical survivors were dubbed white hole remnants, the theoretical mirror opposites of black holes. Where black holes consume, white holes expel. Where black holes trap, white holes release. In this vision, the death of a black hole is not the end, but a transformation, a rebirth. When the black hole's mass dwindles to the quantum scale, the process could reverse. The horizon might dissolve, freeing the information it once held in a final, radiant sigh. Other theorists went further still. They asked a more radical question. What if the evaporation of a black hole does not simply release information, but opens a passage? Quantum physics, with its strange tolerance for tunnels and fluctuations, allows particles to pass through barriers that should be impassable. This phenomenon, known as quantum tunneling, governs everything from radioactive decay to the fusion in stars. Some researchers now imagine that as a black hole nears its final breath, quantum tunneling might occur on a cosmic scale. The imploding core could tunnel through space-time itself, re-emerging not in this universe, but in another. In such a scenario, the interior of a black hole becomes a bridge, a quantum throat linking realities. Its death in one universe becomes the birth of another. The information is not lost, it simply migrates, carried across a boundary invisible to us. From this seed grew new frameworks of thought, none more intriguing than loop quantum gravity, a theory that seeks to reconcile Einstein's smooth spacetime with the granular fabric of quantum mechanics. In this model, space and time are not continuous but woven from tiny loops, Planck-sized grains of geometry. Under extreme conditions, such as inside a collapsing star, these loops resist infinite compression. Gravity still pulls inward, but beyond a certain threshold, the quantum structure of space-time pushes back. The result is a cosmic rebound, a collapse that halts before reaching true singularity. In place of an infinite point, a Planck star is born. A Planck star is an object of unimaginable density and minute scale, existing in a quantum limbo. Trapped within the black hole's event horizon, it stores the information of all that ever fell in, compressed into the smallest possible form allowed by physics. Over vast epochs, as Hawking radiation drains the black hole's mass, the horizon shrinks until it meets the Planck star. And then, suddenly, the black hole explodes outward, releasing the trapped information in a burst of radiation and particles. This process, while purely theoretical, has captured the imagination of cosmologists. It hints at a universe that is not wasteful but cyclical, where even destruction is merely preparation for creation. Some have speculated that the Big Bang itself might have been such an event, the explosion not of a void, but of a black hole in another cosmos. If every black hole ends as a white hole, and if each white hole erupts as a new space-time, then reality could be an infinite web of birth and collapse, a multiverse of recursive creation. In this vision, black holes are not tombs, but wombs. Each one, a seed of Genesis planted in the dark soil of gravity. Each one, a potential universe curled within itself, waiting for the long ages of evaporation to unlock its moment of rebirth. It is a poetic possibility that the same physical laws that destroy stars also give rise to entire worlds. But beneath the poetry lies rigorous speculation. Loop quantum gravity's equations indeed allow such rebounds. The challenge remains, can these ideas be tested, or will they remain in the realm of mathematical dreams? Some researchers, searching for hints, have proposed looking for echoes in gravitational waves, faint, delayed ripples that could follow the main signal of a black hole merger. Such echoes might arise if the event horizon is not a perfect one-way surface, but something with internal structure, a thin membrane capable of reflection. If detected, these ripples could signal that the black hole's interior is not empty, but active, alive with quantum behavior. So far, no conclusive evidence has been found. Yet, in the silence between detections, the mystery deepens. For even the absence of evidence carries its own message, that the frontier between relativity and quantum mechanics remains unresolved, a frontier as vast and invisible as the horizons we gaze upon. And so the paradox persists, each answer only birthing further questions. If black holes can evaporate, do they leave a trace? If information escapes, where does it go? If every black hole seeds a universe, is our own cosmos the offspring of some ancient collapse? The philosophical weight of such questions presses against human comprehension. To imagine that reality itself may reproduce, that creation and destruction are merely two phases of the same cosmic rhythm, is to stand at the edge of metaphysics. In the dark halls of theoretical physics, diagrams sprawl like constellations. Equations loop into infinity. Somewhere, a physicist stares at a chalkboard and wonders if the event horizon is not a wall, but a mirror, reflecting existence back upon itself. If true, then each black hole carries within it not an ending, but an origin, a silent promise that even in the universe's deepest voids, something persists. Not matter, not light, but the continuity of being. And in this continuity, the universe becomes not a collection of objects, but a living pattern, folding, collapsing, and blooming again, endlessly. The whole that should not exist may, in the end, be the universe's most natural creation, a place where death becomes indistinguishable from birth, where the final whisper of one cosmos becomes the first heartbeat of another. As the narrator's voice falls to silence, the screen fades to a slow pulse of light, the echo of an idea that refuses to die. Somewhere, in the darkness between stars, the most mind-blowing hole in the universe continues to hum, not with destruction, but with the quiet music of creation. There are moments in the history of thought when the human mind seems to step beyond its own shadow, when equations begin to hum with the rhythm of creation itself. This chapter, begins in that quiet tension, at the edge where physics folds. Back upon philosophy and reality itself begins to look like an idea dreaming of forming the cold architecture of general relativity. Space-time is not a static stage. It bends, stretches, and collapses under the weight of energy and mass. Where the equations of Einstein converge into impossible curvature, a door appears, the Einstein-Rosen bridge in 1935. Einstein and his collaborator Nathan Rosen discovered that the equations describing a black hole contain another passage, a mirror, mouth on the other side of the singularity, a tunnel, linking two regions of space-time, symmetrical and ghostly, like the reflection of a universe in its own event horizon. But this bridge, in the pure language of mathematics, is fleeting. In reality, such a structure collapses too fast for anything to pass through. Its throat pinches shut faster than light could ever travel, leaving only the ghost of a connection, a cosmic throat that never breathes. Still, this idea that the universe might fold upon itself to create passages between distant realms never died. It evolved. It whispered into the minds of physicists and dreamers who saw in relativity not just geometry, but possibility. In the late 20th century, new mathematics emerged. Physicists like Kip Thorne, Michael Morris, and Ulvi Yurtsever began to imagine how these bridges could stay open, how space-time could be held apart, stretched like a delicate film, stabilized by something the cosmos itself rarely allows. Negative energy exotic matter, a form of energy with pressure less than vacuum itself, it appears, only in the smallest fluctuations of quantum fields, the Casimir effect, where two mirrors placed close together experience a faint attraction as virtual particles are squeezed out of existence. Between them, in these infinitesimal quantum tremors, some saw a potential lifeline, a mechanism that might hold open a wormhole, a traversable tunnel through the fabric of reality, a path not just across space, but between times. If such a structure could exist, it would rewrite causality. Messages could slip through from the future to the past. Journeys could begin before they were conceived. But nature, so far, has offered no hint that such architecture is allowed. Every law we know seems to conspire against it, and yet, each discovery at the edge of knowledge leaves a small crack in certainty. What if the universe's refusal to show us a wormhole is not proof of absence, but of scale? That these tunnels are simply too small, too quantum to be seen? In another wing of theoretical physics, a different kind of bridge began to form. Not through space, but through entanglement. In 2013, Juan Maldacena and Leonard Susskind proposed an idea that felt almost metaphysical in its elegance. They called it ER-Schacht. EPR are the symbols linked two of the strangest discoveries in modern science. ER, the Einstein-Rosen bridge, the classical wormhole EPR, the Einstein-Podolsky-Rosen paradox, describing quantum entanglement, where two particles, even when separated by galaxies, remain mysteriously connected. The conjecture claimed that these are not separate phenomena at all, that every pair of entangled particles is, in fact, joined by a microscopic wormhole, a quantum thread, linking their fates through spacetime's hidden geometry. If this is true, then spacetime itself might be nothing more than the sum of all entanglement, a grand tapestry woven by the invisible relationships between particles. Every connection, a tiny bridge. Every measurement, a tug on the threads of reality. This is not mere metaphor. In advanced formulations of quantum gravity, the mathematics suggests that geometry, the thing we call space, emerges from quantum information. That distance and dimension are illusions born from how information is entangled. Spacetime, then, is not a container, it is a conversation. Meanwhile, a separate path of reasoning, carved by the language of relativity, points toward an even stranger symmetry. That perhaps the universe itself began not with a singularity, but with a white hole. In the equations, a white hole is the time reverse of a black hole. Where a black hole draws matter inward, a white hole expels it outward. It cannot be entered from the outside. It only erupts from within. If such an object existed, it would appear as a cosmic fountain, a flood of light and energy emerging from a point that cannot be approached. Some cosmologists, among them Carlo Rovelli and Francesca Vidotto, have suggested that our own Big Bang might have been the birth cry of such an event. A white hole, emerging from the death of a black hole in another universe. A bridge not between two regions of space, but between two epochs of existence in their model. When a black hole collapses beyond quantum scales, gravity's pull no longer grows infinite. Instead, quantum pressure pushes back. The singularity rebounds for a timeless moment. It exists as a Planck star, a structure smaller than an atom, but containing the memory of a sun. Then, over eons, the rebound completes, and the energy once trapped inside re-emerges as a new universe. If so, the cosmos itself may be a recursive structure. Every black hole the seed of another creation, every white hole the blossom of a dying star's echo, an infinite orchard of universes, growing from the ashes of others. The idea is audacious, but it arises not from fantasy, from equations written in the language of loop quantum gravity, a framework that quantizes space-time itself. In this model, space is not smooth but grainy, woven from loops of energy no smaller than the Planck length. And in this discrete geometry, infinities cannot exist. Singularities dissolve. Collapse gives way to Bounce Ravelli once described it as a universe that learns to avoid its own destruction, a cosmos not doomed to end in blackness, but to transform. To remember as these theories multiplied, from wormholes to Planck stars to quantum threads, a new picture began to form, one that blurs the distinction between physics and philosophy. The holographic principle, proposed by Gerard 't Hooft and expanded by Leonard Susskind, added another layer to this cosmic architecture. It suggested that all the information contained within a region of space could be encoded on its boundary. Like a hologram, where a two-dimensional surface contains a perfect illusion of three-dimensional depth, applied to black holes, it offered a solution to the information paradox. Perhaps nothing is truly lost. Perhaps everything that falls into a black hole is inscribed on its surface, encoded in the faint quantum fluctuations of its event horizon reality. Then might not be what it seems, not a volume of matter, but a projection from the edge of space-time itself later. The ADS-CFT correspondence, discovered by Maldacena, gave mathematical flesh to this idea. A full quantum theory existing on a flat surface could describe a gravitational universe within. The boundary creates the interior, the image creates the object, the universe becomes its own reflection. This, perhaps, is the most profound inversion in modern physics, that what we experience as the three-dimensional world may be an emergent illusion, a grand holographic projection from a deeper, non-local fabric of information. In this view, matter and geometry are not separate. They are patterns in the same field of information reality, as strange as it sounds, maybe more like a thought than a thing, a process of self-relation. A story the universe tells itself. Each of these theories, the wormholes, the white holes, the holograms, the entanglements, are not separate answers, but facets of the same question: what is space-time? What is the architecture behind the appearance of reality? For centuries, humanity believed the cosmos was made of substance, of matter, of stars, of light. But as our mathematics deepens, the universe reveals itself as something more abstract, more elusive, a web of information and relationships, structured by symmetry and bound by paradox. The more precisely scientists measure, the less the cosmos behaves like a mechanism. It behaves instead like an idea obeying its own internal logic, a thought that evolves, collapses, and reflects upon itself through the medium of energy and time. Perhaps the most mind-blowing whole is not an object out there among the galaxies. Perhaps it is the gap in our comprehension, a hole not in space, but in understanding, where reason reaches its edge and peers into the silence beyond. For even the most advanced equations remain shadows of what they describe: the Einstein-Rosen bridge, the Planck star, the holographic horizon, all are metaphors dressed in mathematics. Each one reaches towards something that resists being known, a truth that hides not behind distance, but behind perspective. In the final images of this cosmic architecture, one sees a pattern repeating across scales, the same geometry of connection, in atoms, in stars, in the curvature of galaxies. It is as if the universe were a fractal, thought a mind endlessly unfolding. into new forms of self-awareness. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. Perhaps what he meant was this, that in the act of understanding, the universe becomes conscious of itself, that every equation written, every particle measured is part of the cosmos reflecting upon its own existence. If so, then the architecture beyond space-time is not somewhere else. It is here, in the patterns of thought, the shapes of theories, the quiet astonishment that arises when a mind contemplates infinity. The black hole, once feared as the grave of physics, may instead be the doorway through which the universe looks back upon itself. And in that reflection, the boundaries dissolve. Matter becomes information, space becomes relation, and the cosmos, vast, ancient and mysterious, becomes a single, endless act of creation. The search for truth often begins not with discovery, but with silence, a silence broken only by the hum of machines staring into the dark around the world. A new generation of instruments now listens to the faintest echoes of creation, each one built to peer deeper into the abyss, to trace the shadows of gravity itself as it bends, breathes, and flickers at the edge of existence. The Event Horizon Telescope, a network of radio observatories spread across the planet, once captured humanity's first glimpse of the unseeable in 2019. Its lens of synchronized antennas stitched together an image of the black hole in galaxy M87, 55 million light-years away, a ring of fire suspended in cosmic darkness, where light spirals but never escapes. It was not merely a photograph, it was the boundary of understanding made visible, but the story did not end there. The EHT has evolved. New stations have joined, across the globe, in Greenland, in Africa, in the high plateaus of the Andes, turning the Earth itself into one vast eye. This next-generation array aims to do what once belonged only to imagination, capture black holes in motion, to film the dance of light as matter falls inward, to witness the turbulence of magnetic fields twisting space like liquid glass. Real-time black hole dynamics, a phrase that once sounded like fiction, now lies on the edge of engineering in these new observations. Physicists hope to measure how black holes feed, flare, and breathe. To test Einstein's equations under the most extreme pressures nature allows, every fluctuation of brightness becomes a test of relativity. Every photon that escapes from the brink carries the fingerprint of gravity's geometry. And yet, the deeper they look, the more the abyss stares back. Because each refinement in resolution brings new riddles, the shadow seems to shift. The jets pulse with patterns no simulation can yet predict. The boundary between observation and imagination grows thin. Far from Earth, another instrument is waiting to unfold. It will not look at light at all, but at the trembling fabric of space itself. LISA, the Laser Interferometer Space Antenna. A mission led by ESA with NASA's support will float in the quiet vacuum of interplanetary space, 3 satellites drifting in a perfect triangle, 5 million kilometers apart, connected by laser beams so precise they can measure distortions smaller than a proton's width. LISA will listen for the deepest symphonies the universe has ever composed. Gravitational waves, not the brief, thunderous bursts from colliding black holes we already know, but the long, low murmurs of cosmic cataclysms, billions of years-old binary supermassive black holes orbiting one another, entire galaxies merging, space-time rippling like water, disturbed by the fall of a single stone. Each wave carries memory, a record of motion through the invisible geometry that binds everything. From those vibrations, scientists will reconstruct the stories of creation and destruction written into space-time itself. It is as though the cosmos, for the first time, will speak its autobiography through gravity's music, and perhaps within that signal will lie something even, stranger anomalies, in the waveform that could reveal new physics. Hints of exotic compact objects, echoes that repeat where they shouldn't, patterns that whisper of wormholes or Planck scale, remnants. Each detection will be not only a discovery, but a question. What else could bend space in this way? At a quieter point in the sky, another telescope continues to look backward in time. The James Webb Space Telescope, orbiting beyond the moon's shadow, is searching for the faint light of the first quasars. Its gold mirrors, cold and patient, capture photons that began their journey over 13 billion years ago. Some of these quasars may hide the universe's first black holes, primordial giants born from collapsing clouds before galaxies even existed. Astronomers call them baby holes, though their masses defy the name. Hundreds of millions of suns compressed into seeds only a few 100 million years after the Big Bang. How such titans could form so quickly remains one of cosmology's sharpest mysteries. Did they grow from collapsing stars? Or did space-time itself give birth to them? Direct collapses of dark matter or quantum fields in the universe's infancy. Webb's infrared eyes peer through cosmic dust, studying their spectra, searching for signs of accretion, magnetic flows, and chemical fingerprints. Each discovery challenges the boundary of theory. Each ancient glow is a page from the early universe's diary, where gravity was still learning how to write in the dark between those stars. Physicists suspect there may be clues not only to how black holes formed, but to why the universe looks the way it does. For in their birth may lie the same laws that govern cosmic evolution itself. Black holes are no longer the monsters of mythology. They are the architects of structure galaxies orbit their gravity. Time itself curves to their command, but the quest does not stop at observation on Earth. In laboratories no larger than a room, physicists attempt something even more ambitious: to recreate the fabric of space-time itself. Quantum computers, devices that manipulate superpositions and entanglement, are becoming miniature universes of their own. In 2022, researchers at Caltech and Google simulated the behavior of a traversable wormhole within a quantum system. It was not a physical tunnel through space, but a mathematical correspondence between entangled qubits that mirrored the equations of a wormhole's geometry. When information was sent into one side of the entangled system, it appeared to re-emerge on the other, as if it had traveled through an invisible bridge. This experiment, though symbolic, offered something profound. It hinted that wormholes and entanglement may indeed be two sides of the same phenomenon, that space-time itself could be an emergent network, a vast quantum web whose structure arises from relationships, not from substance. In other words, to build a wormhole, one does not need to tear space apart. One only needs to understand entanglement deeply enough. Such quantum simulations are now expanding. Researchers are using trapped ions, superconducting circuits, and ultra-cold atoms to model the physics of curved space-time, black hole evaporation, and quantum gravity. Within these artificial microcosms, they hope to glimpse the unity between general relativity and quantum mechanics, a harmony nature still hides. The ultimate goal is not to create a wormhole or a black hole in a lab. It is to understand how space-time itself arises from the dance of information, to reveal the secret code that translates thought into form. This pursuit has become as philosophical as it is physical at times. It feels as if humanity is not observing the universe, but the universe is observing itself through humanity. Every telescope, every detector, every algorithm is an extension of cosmic curiosity. Instruments built by stardust to look back upon its origin. When the Event Horizon Telescope stares into Sagittarius A, it is matter watching the abyss from which it came. When LISA's lasers measure the breadth of space, it is the universe listening to its own pulse. When quantum computers simulate space-time, it is information modeling its own reflection. Science becomes self-awareness at a cosmic scale. Each discovery a neuron firing in the brain of creation, and yet, beneath all this, there remains humility. Because even as we extend our senses into the infinite, the mystery only deepens for every image captured. 10 new shadows appear for every wave detected. 1,000 questions echo back. Perhaps that is the nature of knowledge itself, an endless horizon that recedes as it is approached, like the event horizon of a black hole, forever visible, never reachable in the coming decades. New tools will join this cosmic symphony. Projects like the Next Generation EHT will refine imaging of black holes to resolutions 100 times sharper. The Square Kilometre Array will map the universe's radio heartbeat across cosmic time, and LISA's signals will merge with data from LIGO and Virgo, creating a true gravitational atlas of the universe together. They will not only test Einstein's equations, they will probe the edges where those equations begin to break, where classical geometry gives way to quantum foams. and space-time becomes a probabilistic blur. Each machine is a kind of prayer, engineered from curiosity and patience. They are not simply devices to collect data. They are mirrors, reflecting what the universe dares to dream of itself. The human gaze, magnified through silicon and steel, has become a cosmic instrument through it. The abyss gazes back, not as a void, but as a mirror reflecting consciousness. The cosmos, it seems, does not merely exist, it experiences. And so, when one stands beneath the night sky, beneath the same stars that feed the telescopes and charge the equations, one might feel the quiet symmetry of it all, that we are not apart from the darkness, but expressions of it, that the black holes we study are not distant objects, but the same logic of existence that binds every atom of our being, from the hum of quantum computers to the silent wings of space antennas drifting through the void. Humanity's search is becoming something larger than science. It is a continuation of the universe's own desire to know itself. Every new telescope, every lens, every mirror, all are reflections of that single cosmic act, the drive to turn chaos into understanding, silence into meaning, darkness into vision, and so the narrator's voice softens, almost as if the cosmos itself were whispering through it. Every new telescope is not just a machine, it is a mirror, reflecting what the universe dares to dream of itself. The film slows, the motion of galaxies fades into stillness, the light bends, softens, then disappears, before the viewer stretches a horizon of silence, a dark, infinite sphere of absence, a black hole, calm and eternal, breathing quietly in the deep for centuries. The idea of such an object belonged only to imagination, a mathematical ghost, a product of equations that dared to suggest the impossible. Now it is a reality written in radio waves, in gravitational echoes, in the quiet hum of cosmic data. And yet, even as it becomes more real, it becomes more mysterious, because every new observation, every photon caught circling the abyss, only deepens the question: what truly lies within? The story of the whole has evolved with humanity's gaze. In the 18th century, it was a dark star, an unseen sun whose gravity could swallow its own light. By the 20th, it became a singularity, the end point of collapse, where space-time breaks. By the 21st, it became a paradox, a place where physics itself begins to dream. And now, as the models converge, another vision begins to take shape. A possibility whispered by both cosmologists and philosophers alike, that these cosmic abysses are not the ends of matter, but the beginnings of something greater. If gravity can fold a star into a single point, if space-time can curve until it seals light itself, then perhaps collapse is not destruction, but transformation. Perhaps every death in the universe is also an act of creation. Modern theories have begun to suggest as much. Loop quantum gravity, string cosmology, and the mathematics of quantum bounce all point toward a singular idea: that the singularity at the heart of a black hole may never truly form. Instead, as matter collapses, the density grows. But before infinity is reached, quantum geometry intervenes. Space-time resists its own end. It rebounds theoretical. Models call this rebirth a Planck star, an ultra-dense core where gravity and quantum pressure balance in perfect tension. To an outside observer, this rebound might take longer than the age of the universe, frozen behind an event horizon. But within, in its own distorted timeline, the process may unfold in an instant. The collapse turns inside out. A new expansion begins. To some physicists, this expansion is indistinguishable from a Big Bang, a universe born from the death of another cosmos, nested within a cosmos. A recursive creation, endlessly mirrored. If that is true, then every black hole is a seed, every void, a womb, and our own universe, with all its galaxies, stars, and minds, might itself have once emerged from the final heartbeat of another dying world. This possibility transforms everything. The image of the black hole, once a symbol of annihilation, becomes one of creation's deepest metaphors. The universe, then, is not a static expanse, but an evolving thought, a cycle of falling and becoming, of compression and release, a breathing cosmos, where death and genesis are not opposites, but phases of the same cosmic rhythm. Astrophysicists have begun to explore how such a process might be encoded in nature, through quantum tunneling, through entropy conservation, through information that refuses to vanish even beyond the event horizon. Stephen Hawking's work on black hole evaporation laid the foundation. Information, he argued, may never be destroyed, only transformed, hidden within radiation, encoded in patterns too subtle to yet decode. And if that law holds true, then not even the black hole can erase the universe's memory. Every collapse contains its history, folded into energy, waiting to be reborn. Every horizon becomes a boundary not between life and death, but between knowing and becoming. From this perspective, a black hole is not only a cosmic object, it is a philosophical mirror, a reflection of the human condition, for within every consciousness lies a similar horizon, a boundary where thought falls inward, beyond language, beyond understanding. Memories spiral, identities compress, time slows, and somewhere in that silent interior, new insight emerges, unbidden, radiant, unexplainable. Human thought collapses and expands. Just as the cosmos does, ideas die and are reborn. Each mind becomes a miniature universe, filled with its own singularities, its own unseen depths. In this sense, consciousness itself may be a kind of space-time, curved by memory, shaped by gravity-like emotion, threaded by the entanglement of experience. Perhaps then, the true whole that thinks is not out there in the stars. It is within the awareness that contemplates them. Philosophers of physics, from Wheeler to Penrose, from Rovelli to Susskind, have begun to glimpse this symmetry between mind and matter. The structure of thought and the structure of space-time share a strange logic. Both are networks of relationships, not things. Both are built from information. Both depend on observation for meaning. In quantum mechanics, a particle exists as probability until it is measured. In consciousness, an idea exists as possibility until it is understood in both. Reality crystallizes through awareness. Could it be then that the universe is not simply made of matter, but of information thinking itself into form? If so, the black hole, the place where information condenses, scrambles, and re-emerges, may be the ultimate metaphor for the mind of the cosmos, the whole that thinks. This notion is not mystical, it is mathematical. The holographic principle, derived from black hole thermodynamics, suggests that everything within a region of space can be encoded on its boundary, as if the universe were a projection from a deeper, two-dimensional information field. Every atom, every galaxy, every thought, all written upon the surface of space-time like code on the skin of infinity to observers within. Reality feels three-dimensional, but from a higher view, it might be something else entirely, a simulation, a reflection, a thought that has learned to observe itself in this view. The black hole is not an exception to the universe. It is its essence made visible, a window into the logic by which existence sustains itself. And yet, for all the equations and theories, one truth remains untouched. No telescope, no computer, no human mind has yet seen beyond the event horizon. The boundary remains absolute, a horizon not only of space, but of meaning. Perhaps that is what gives the black hole its beauty. It is a question that cannot be answered, a silence that cannot be translated. It draws the human mind toward it, not to solve it, but to feel its enormity, to stand at the edge of the unknowable and realize that knowing has limits, that beyond comprehension lies wonder, and beyond wonder lies peace. The narrator's voice slows, softer now, as if speaking across light years of reflection. The black hole, once feared, now revered, has become the symbol of everything the universe both conceals and reveals. It teaches that reality is not defined by presence, but by absence, not by what is visible, but by what resists visibility in its shadow. The cosmos speaks a quiet truth, that every fall is a return, every silence hides a song, every end is a beginning, waiting to be named. From the death of a star comes the birth of a whole. From the death of a whole, perhaps the birth of a universe, and within that cycle, consciousness awakens, matter that has learned to reflect on its own impermanence. Perhaps this is the true architecture of existence, Not infinite matter, but infinite imagination. A cosmos that does not merely expand through space, but through awareness, each black hole a neuron, each galaxy a thought, each observer a reflection of the same unending process. As the camera drifts closer toward the horizon of the black hole, the swirl of gas slows, then stills. Time itself seems to stretch. The light fades until nothing remains but darkness. Not empty, but full, dense with possibility, the narrator whispers, barely audible against the hum of the cosmos. Some holes swallow light, others swallow certainty, but the greatest of them all swallows the boundary between what is known and what can only be dreamed. The screen goes black, the hum fades, and for a long moment, longer than thought, the only thing left is silence, a silence that feels alive.